Hey guys, welcome to today's class. Have fun.
Hello, welcome to class today. Today I'll be talking about atomic structure, and the class will be divided into two. This is the first class, which is atomic structure 1. So basically we'll be looking at what the atom is made up of. In the previous class on molecules, atoms, I was able to define what an atom is as the smallest indivisible particle of an element which can take part in a chemical reaction and still retain the chemical properties of the element. So when we're talking about the atom now further we want to dwell into what an atom is composed of. So we have basically three atomic subparticles. We have the electrons, we have the protons, and we have the neutrons. So when we're talking of an atom now, you have this basic knowledge of the atom. This is our nucleus. This is the nucleus. And the nucleus is composed of the proton and the neutron. Now, revolving around the center mass of an atom is what we refer to as the electron. So basically, an atom is made up of three main subparticles, which is the electron, the proton, and the neutron, which we'll be looking at very quickly. So the first subparticle we'll be talking about is the electron. So the electron, which was discovered by J.J. Thomson. Now we need to have a brief overview of these particles before we can understand basically how we'll be using them in subsequent classes. So an electron was discovered from a simple experiment which J.J. Thomson carried out years back, which is the famous experiment known as the Cathode Ray Experiments. So in this experiment, J.J. Thomson was able to conclude that electrons were present in all matter. So this experiment was a very simple experiment which Thomson carried out. So we have something like this, and we have I just want to give us a good interpretation of the experiment. We have a cathode. Okay, so J.J. Thomson carried this particular experiment to determine the presence of an electron as a subparticle of an atom. So in this experiment known as the cathode ray experiment, which I said earlier, what he simply did was he subjected a gas to very low pressures, because gases at low pressures was able to conduct electricity, and it has been proven that electricity is as a result of the carriage or transfer of electrons, so which he wanted to prove using gases. So this gas at very low pressures, they were subjected to high voltage or potential differences. So it was observed that from a certain point where he ejected cathode rays, he observed that there were movements in straight lines. This movement in straight lines was due to the particle called the electron. So there are movements. So J.J. Thomson was able to discover that cathode rays, number one, cathode rays travel in straight lines. These cathode rays are what we know as electrons now. They travel in straight lines. They are composed of negatively charged particles. They travel in straight lines. They have negative charges. They are capable of producing motion. So In this experiment, J.J. Thomson discovered the electron. So, and in summary now, the electron is a negative charge. This is the charge of the electron, minus 1.6 times 10 raised to the power minus 19 coulombs. So in subsequent research also, R.A. Millikan was able to discover, he was the one who discovered the charge. So from there, they were able to discover the mass of an electron. So the specific charge of an electron, that is the charge to mass ratio, is 1.76 times 10 raised to the power minus 11. So from this simple formula, it is the charge over mass. And since we know the specific charge ratio to be 1.76 times 10 raised to the power minus 10 raised to the power 11 coulombs per kg, and we discovered the charge, so they were able to determine the mass of an electron, and the mass of an electron is 9.1 times 10 raised to the power minus 31 kilogram, which is very negligible. Okay, so we also have the protons and the neutrons. Like I said earlier, we have the electron, the proton, and the neutron. I've been able to discuss the electron, which is a negatively charged particle. So also J.J. Thomson, in further experiments, he was able to discover the proton in this same experiment, which is the cathode ray experiment. So in further development to the experiment, he discovered that there were also opposite charges, that is opposite flow of particles. So in this first case, he discovered these cathode rays which moved in a certain direction towards the positive electrode of the tube. So also he discovered a reddish glow, which was due to the existence of protons in this experimental setup. So this positive charge, which is moving towards the negative electrode of the discharge tube, is what we refer to as protons. So protons also have a specific charge. The charge to mass is 9.58 times 10 raised to the power 7 coulombs per kilogram. And this is the mass of the proton. The mass of the proton is 1.673 times 10 raised to the power minus 27. So comparing the mass of the proton now to the electron, the proton is 1,840 times heavier than the electron, and it carries a positive charge. So the last subparticle of the atom, which is the neutron. The neutron was also discovered by a scientist called James Chadwick in 1932. So in this simple experiment he carried out, he was able to discover that the neutron has a mass which is equal to the mass of the proton, and he was able to discover that the neutron has a neutral charge. Sorry, this is neutral. Neutrons are neutrally charged particles. So in summary of this, we've been able to establish the three basic So in terms of the location now, the proton is found inside the nucleus, the electron is found outside the nucleus, the neutron is also found inside the nucleus. The proton has a positive charge, the electron has a negative charge, the neutron has no charge, it is neutral. So their relative mass, the proton is 1. Like I said, the neutron and the proton have an equal mass, and the mass of the electron is negligible. So very quickly now, I'll be looking at various atomic theories. We have the atomic theories. So discovery of these various subparticles, which are the proton, the neutron, and the electron, was brought about as a result of experiments, theories from time to time, and various models of the atoms which scientists put forward. And the very first theory of atomic structure is known as Dalton's atomic theory, which was put forward by a scientist in the year 1808, John Dalton, the British scientist. So Dalton was able to come out with various postulates which are well known and which we are expected to know as we're making use of them. The first postulate of the Dalton's atomic theory is all elements are made up of small indivisible particles called atom. So the first thing Dalton was able to put forward is that every element, say carbon for example, is made up of atoms. Like I said in subsequent classes, the atom is the smallest particle. So Dalton was able to establish this. So Dalton also established that atoms can neither be created nor destroyed. So he simply said atoms can neither be created nor destroyed, meaning that atoms are the smallest unit of any chemical reaction. So also Dalton postulated that atoms of the same elements are alike in every aspect and differ from atoms of other elements. What does this mean? You have an atom of carbon and you have another atom of carbon, let's say from different locations. So what Dalton simply told us was that the atoms of the same elements are alike, while atoms of an element with respect to another element are totally different. Okay. Dalton also postulated that when atoms combine with other atoms, they do so in simple ratios. So what Dalton was simply saying is, let's say when carbon is to react with oxygen, they do so in simple ratios, let's say ratio 1 to 2, to form carbon dioxide or carbon monoxide. So atoms combine in simple ratios to form atoms. Then the last one here is that all chemical changes result from the combination or separation of atoms. So Dalton also discovered that, or postulated that, chemical changes result from the combination or separation of atoms. Since atoms are the smallest units, any chemical change must occur due to maybe the addition of one or more atoms or the division of one or two atoms. So this atomic theories put forward by Dalton was deduced from the various laws, the laws of conservation of mass, definite proportions, multiple proportions, which I explained in previous class. So this law was over time found to be not very much effective. So due to some limitations of this theory, this led to the modification of Dalton's atomic theory. So it was found out that these 5 theories or laws put forward by Dalton were not effective. So which led to the modification of Dalton's atomic theory. So recall that the first theory Dalton put forward was that all elements are made up of small indivisible particles called atoms. So here I'll simply be explaining how the theory was disproved. So the first law which Dalton put forward, all elements are made up of small indivisible particles called atoms. So this statement is wrong because we are made to understand now that an atom can be further divided into proton, neutron, and electron. So the first statement of Dalton is wrong. Atoms can further be divided into more indivisible particles, proton, neutron, and electron. So the second statement by Dalton was that atoms can neither be created nor destroyed. So this statement holds good to a certain level, but due to the discovery of radioactivity, this theory put forward by Dalton is no longer correct because radioactivity has to do with fusion and fission, and as a result of this, atoms can be destroyed, they can be created, and they can also be manipulated for various chemical purposes. So the third statement put forward by Dalton was atoms of the same elements are alike in every aspect. But Dalton said if you find an atom of carbon, another atom of carbon, they are always the same. So this also is wrong as a result of the discovery of isotopy. When we're talking about isotopy now, isotopy are atoms of different atoms of the same element which exhibit different chemical properties. Simply put, when we talk about an isotope, you have carbon and you have another carbon. There are two isotopes of carbon. You have two main isotopes of carbon, carbon 12 and carbon 14. So this is the same carbon, but they have different atomic masses. So as a result of the different atomic masses, they have different number of neutrons and different ways in which they will occur in reactions. So that statement by Dalton was also proved wrong as a result of the establishment of isotopy. So I'll also explain what isotopy means in subsequent topics here. So another statement put forward by Dalton was that a chemical reaction is as a result of the combination of atoms in small whole numbers. So this has also been put forward as incorrect due to the establishment of inorganic compounds. So in inorganic compounds now, they are very, very large compounds or molecules which are formed, which are your proteins, your fats, your glucose. Dalton said when chemical reactions occur, they occur in simple ratios, but in organic compounds now, you have thousands of atoms coming together to form various chemical compounds, molecules. So, yeah, I'll be able to explain the atomic theories which was put forward and the modifications to each of these statements which we should take note of. So another quick thing we'll be looking at are the various models of the atom. And we have three basic models of the atom. We have the Thomson's model, the J.D. Thomson. We have Rutherford's model of the atom, and we have Neil Bohr's model of the atom. So the first model of the atom is Thomson's model of the atom. First model is Thomson. Now Thomson's model of the atom is a very simple model. So in 1898, J.D. Thomson put forward his own model of the atom. He simply said that an atom is composed of a sphere of positive charges embedded in electrons which are also negative charges. So what Thomson put forward was that an atom is a sphere or a ball of both positive charges and negative charges. So this model of the atom is a very let's say limited model of the atom because it could not explain further experiments. It could not stand the test of further experiments. So also we have another model of the atom which is Rutherford. So we have Rutherford's model of the atom. So in Rutherford's model of the atom, this is a more advanced model when compared to J.D. Thomson's model. So in this model, he carried out a very simple experiment. So in Rutherford's model, he carried out an experiment. Use the microscope. So in Rutherford's model of the atom, he carried out an experiment using alpha particles. Alpha particles are positive charges. So they bombarded this thin foil of gold with alpha particles at very high speeds, moving in straight paths to hit this gold foil. So in this discovery, Rutherford was able to discover that some particles of this atom, of this alpha particle, which are positively charged, pass through this gold foil. This is one fraction. Then another fraction, this were scattered along the path. So this brought Rutherford to a conclusion. So Rutherford was able to deduce that an atom consists of a very large amount of space, because these alpha particles were able to either pass through the foil or scatter themselves. So this is a result of a large amount of space in atoms. In Rutherford's model, an atom consists largely of empty space. An atom has a central mass. So this central mass is as a result of the neutron and the proton. So it was also Rutherford that was able to establish that we have, an orbital system of atoms. So Rutherford's model now was able to establish that as a result of these alpha particles passing through this center mass, we have a central mass consist of neutron and proton, and we have an external area in which electrons orbit around. So these particles that pass through here, which are positive particles, some of them pass through here. It was also observed that those ones which were deflected away were due to the concentrated positive charge of the nucleus. So the nucleus is relatively positive in charge, and those ones that were able to deflect was as a result of the external, external field now of negative particles, which is as a result of the electrons. So Rutherford's model is a very straightforward model which can be compared to the solar system, in which we have an atom made up of a central mass and electrons which orbit around the system, like the Earth orbits around the sun. So this is what the Rutherford model is all about. So lastly, we have the Bohr's model of the atom. So in Bohr's model of the atom now, in Bohr's model of the atom, he took a more advanced approach to be able to establish the existence of the particles, the proton, the neutron, and the electron. So in Bohr's model of the atom, he carried out experiments with respect to the knowledge on quantum theories. So what he was able to assume from his experiments was that the Rutherford's model of the atom was correct, that every electron exists in circular orbits. He was able to establish that electrons exist in circular orbits. He also established that each electron emits energy while they move from one orbit to another orbit. Let's say this is the first orbit and this is the second orbit. So Bohr's model of the atom, he carried out an experiment using hydrogen. He was able to observe that there were various layers of energy in an atom. So as you move forward, you have increasing energy of atoms, of the electrons rather. So Bohr was able to discover that electrons exist in various levels of energy. This is level 1, 2, 3. And that electrons have the ability to jump from one energy level to another energy level in stages. So Bohr's model is a very large and expansive model of the atom. He talked about wave mechanics, talked about quantum theory, and he also brought about energy changes. When you want to move from one level to another, for you to move from level 1 to level 2, you require a certain amount of energy. So Bohr's model of the atom, you have Rutherford's model of the atom, and you have Thomson's model of the atom. So this should give us a brief of the discovery of atomic particles and the structure of an atom. So lastly, we'll be looking at atomic number and mass number. Okay, so when we talk about atomic number, we designate it with Z now. The atomic number of an element is the number of protons in one atom of that element, while the mass number, designated as A, of an atom is the sum of the protons and neutrons in it. So what are we simply talking about now? We have an element X now. I said the atomic number is the number of protons in the atom of that element. So this, which is Z, this is the number of protons, and this is the mass number. The mass number is the addition of protons and neutrons. So atomic number of protons in an atom is also referred to as the atomic number. The mass number is the addition of the proton and neutron. So the mass number of an atom is the sum of its proton and neutrons. So this is a simple illustration. So I'll be giving examples now. So an example now, we have carbon, which has an atomic number of 6, and 6 is its atomic number. We have carbon, we have 1, 2, 3, 4, 5, 6. So it has an atomic number of 6. 1, 2, 3, 4, 5, 6. It has 6 protons, or you can say it has 6 electrons, and it has a mass number of 12. The mass number is the number of protons plus neutron. So if you have the protons to be 6, then it also has 6 electrons, which is 6, 12. So I'll be giving a very broad example. So lastly, I'll be talking about isotopy. So when we talk about isotopy is a phenomenon in which atoms of an element exhibit different mass numbers but have the same atomic number. When we talk about isotopy, this is a simple phenomenon in which atoms of an element has different masses but the same atomic number. A good example of isotopy is what we see in chlorine. Chlorine exhibits isotopy. Carbon also exhibits isotopy. Oxygen also exhibits isotopy. So we can have chlorine. You can have chlorine with atomic mass 35 and another chlorine with atomic mass 37. They have the same atomic number but different masses. This is isotopy. You can also have carbon. We have carbon 12. We have carbon 13. You can also have carbon 14. So they have the same atomic number, different atomic masses. So this is also isotopy. You can also have oxygen. You have oxygen 17 and you have oxygen 16. This is also isotopy. They have the same atomic number, different atomic masses. So quickly we'll be looking at a good example now. So we know that the atomic mass of chlorine is 35.5. Now, the reason for this atomic mass unit is as a result of the isotopic nature of chlorine. Since chlorine has two isotopes, main known isotopes, we have to find a general mass for it. We can't say we want to use 35 or we use 37. We have to find the average mass of the atom. So this was as a result of the chlorine of mass 35 has an abundance of 75% in nature. This has an abundance of 25% in nature. So for the first match, which is 75% abundant in nature, 75% of its mass plus 25% the mass of this gives us 35.5 atomic mass units. So the same thing applies to carbon, to oxygen, and other elements which exhibits isotopy. So we have an example now to lay our hands on. We have a table. These are elements. This is sodium. We don't know these elements. These are unknown. This is neon. This is unknown. This is an ion of sulfur. This is also unknown. We have some of their mass numbers. We have some of the atomic numbers, some of the proton numbers, and also the neutron number and the electron number. So what we are going to be doing here now is we want to be able to fill these gaps. So the first thing to note is that the atomic number is the number of protons, which can also be the number of electrons. But our primary focus is the number of protons. And also recall that the mass number is the number of protons plus the number of electrons. Okay, so using these simple formulas now to figure this. Now, for this first one, we need to find the mass number, the number of protons, and the number of electrons. Now, recall that the atomic number is the number of protons of that element, which means that the number of protons of this element is 11. Since we can also recall that the mass number is the sum of the proton and the neutron, the number of protons plus the number of neutrons, protons plus the number of neutrons is what gives us the number. So on the addition of 11 and 12, we have 23, which is the mass number. And the electron number can also be the number of proton. So the electron number here is so to designate this now, the proton number is 11 and the atomic number, the mass number is 23. So this is done. So you also have another example here now. We have the mass number, the proton number, and the electron number. We need to find the number of neutrons and the atomic number. Recall that the atomic number is a proton. So 17. Now recall that the mass number is the sum of the proton and the neutrons. Since we know the number of protons to be 17, to get our neutrons now, 37 minus 17 will give us the number of neutrons. So we have 20 neutrons. So we're able to establish this element now. And the element with atomic number 17 is chlorine. And this is an isotope of chlorine with proton number, which is 17, and mass of 37. So also be able to establish this. So also another example here, we have mass number 16. We don't know the atomic number. We know the number of protons. The atomic number is the number of protons, which is 8. The mass number is the sum of protons and neutrons. So the mass number minus the proton number will give us the number of neutrons, which is 8. So this can be oxygen. So given an electron of 10 now. So this is an ion of oxygen, which is O2 minus. So we also have another example here. We have the mass number, the atomic number. The number of protons is the atomic number, obviously. So this is 13. To find the neutrons, mass number minus proton number will give us the neutron. So we have 14 as the neutron. So this gives us the elements with atomic number 13. We have aluminium with proton number 13, mass number of 27. It has 10 electrons. Here we have 13 protons. So this gives us so we have 20, 10, 10. The number of protons is the number of atomic number. This is 10. 10 plus 10 gives us 20. So our number of electrons here is also 10. So we have 6, 8, 6. Proton plus neutron gives us the mass number, obviously. But in this case, this is a different case now. So the atomic number is definitely the number of protons, which is 8 plus 6, so yeah, it should be 14. Number of electrons, yeah, 8. In this case, 16 plus 16 gives 32, the mass number. The atomic number is the number of proton. And the number of electrons, 16. In this case also, the mass number is the sum of the proton and the neutron. 10 plus 7, 17. The atomic number is 7. So in summary now, you have oxygen. Now aluminium, yeah, an example from here. Aluminium has 13 protons. It has 13 protons. This is aluminium. On the other hand, when I have Al3+, this has 13 protons. It also has in this case we have Al3+. So in this case here I have also 10 electrons. But in this case now I have 13 protons. I have 14 neutrons. I also have 10 electrons. Yes, sorry, I have 13 electrons. So there's a difference between these two. These are ions, which I've also explained previously. These are charges. When we say plus, we simply say it names electrons. When we say minus, it gives electrons. So in summary now, Al3+ needs 3 electrons. So that's why the number of electrons is shorter, is a shortfall of this. So when we have oxygen now, we have O2 minus. Oxygen has 8 electrons, but the ion in this case has 10 electrons. This 2 minus means it gave 2 electrons. So that should be a wrap on this class. Thank you.
I hope the class was interesting. If you have questions, please drop them in the comment section or send us an email. We will love to help you further. See you in the next class.